First of all, you guys kind of already know what a sequence is. It's really just a list of values. So an infinite sequence, what is an infinite sequence? It is a sequence with an infinite number of terms. Infinite number of terms. And infinite sequences are very easy to spot because they have a dot, dot, dot at the end. Really easy to spot. Okay, and then in 8.1 we actually already studied sequences. We said that they will converge to L if the limit is L. And L is any real number. Any real number. Okay? And a sequence, an infinite sequence will diverge if the limit is infinity or negative infinity or D and E. So I should have had all three of these here. Anytime your limit is infinity, negative infinity, or the limit simply doesn't exist, we would state it's divergent. Divergent sequence. What does it mean? Well, let's take a look at this first example. I think it'll be very clear. This is like example 0 because it's not even a chapter 9 concept yet. Okay, so yours should say A, B, C. Sorry, I think it says D, E, F there. Fix that. Our first example, A is this sequence. If you wanted to, you could plug in numbers. For example, 1, 2, 3, 4, 5. But what you'll notice is that the numbers in the list are all getting closer to 2/3. Why? Because the limit as n goes to infinity of 2n squared minus 5n plus 1 over 3n squared minus 1 is 2/3. See? So all you really have to do is you don't have to make a list and stare at the numbers. You just answer this question, what is the limit? And bam, you've got the convergence value. There it is, 2/3. So you could write a conclusion real quick. This is what you would write. A sub n converges to 2/3. Why? Because the limit's 2/3. Done. I wish series was this simple, but it isn't. Sequences are this simple. Okay? Let's try the next one. What's the limit on that guy? B sub n. Sorry it's a little small. I figured you have it there on your paper, and you can still see it on your paper there. So what's the limit of B sub n? Infinity, right. Notice it's top heavy. Everyone has it there on the paper, right? It says 2n cubed on the top, but 3n squared on the bottom. So clearly it's top heavy. B sub n diverges because LIM, n goes to infinity, 2n cubed minus 5n plus 1 over 3n squared minus 1 is infinity. How about this next one? 2 to the n minus 1 all over n squared. What did you learn back in section 8.3? Who grows faster, 2 to the n or n squared? 2 to the n. 2 to the n is clearly with the larger growth rate. If you did your homework, so you realize that. All exponentials are higher growth rate than all polynomials. Even 2 to the x grows way faster than x to the millionth. Say that again. 2 to the x grows faster than x to the 1 millionth. Okay? So anyway, you can use L'Hopital's rule on this, though, if you just kind of convince me that this is divergent. Watch this. C sub n diverges because LIM, n goes to infinity. I'm getting too lazy to write the function. I'm just going to write C sub n equals infinity. And I just want to show a little work for that. Just to convince the teacher, that I'm not just making that up. This limit is L'Hopital eligible. So you could take the derivative of the top, and you get 2 to the n ln 2. Take the derivative of the bottom, you get 2n. It's L'Hopital eligible again. LIM, n goes to infinity, 2 to the n ln 2 times ln 2 again, all over 2. Well, now it's very, very obvious to me. The bottom is simply 2. The top still has an n. So I just did 2 iterations of L'Hopital. The bottom is now constant, but the top still has that persistent Energizer bunny and that to the end stays there forever as I differentiate. And so this diverges. Okay? I think we should add a little part D to this one. Real simple one. Part D, d sub n is cosine n. D sub n is cosine n. Now, if you try to take the limit as n goes to infinity, what's going to happen? What's going to happen? You're not going to be able to get a limit. So this one is also a divergent case. You would put d sub n diverges because Lim, n goes to infinity, of d sub n does not exist. Cosine has no limit out near infinity. Like there's no meaningful number it approaches. So, like I said here, it diverges if you get infinity or d and e. Here's an example of the d and e case. We would say the sequence diverges. What does it even mean for a sequence to diverge? It means this. If you list out all these numbers, you know, the first term and the second term and the third term, and you plug it in equals 40 in the fourth term, and you look at the 50th term, and you look at the 1000th term, in the first case, they're getting closer to 0.66666. But in the other 3 cases, they're just plain growing. Okay? Or in that last case, they're just misbehaving. -1, +1, -0.9, 0.9. There's no pattern that brings them to a single value. Okay? All right, so pretty easy to do sequence convergence. Super easy. It's just a limit problem. I show you this because we're now going to do series, and it is not the same question. Okay, so first I have to convince you it's not the same question. Maybe you don't know what the difference between a sequence and a series is, but a sequence is basically a list of numbers with commas in between, and a series is a list of numbers with plus signs in between. There's a big difference there. Okay, so let's just take a look at some cases so you can see what I'm saying. What is an infinite series? It is anything that looks like this. Not A1, comma A2, but A1 plus A2, not comma A3, but plus A3, not comma A4, but plus A4, etc. And it goes on forever. That's a series. Eventually you'll reach some term in here called A sub k, but there's terms after that too. In fact, it just goes on forever. It's an infinite series. What makes it a series? The pluses, not commas. How many of you knew that the difference between a sequence and a series was that the sequence had commas and the series had pluses? How many of you knew that? 2 people. Okay? It's supposed to learn that in Algebra 2, but it's been a couple years, right? Okay, what does convergence then mean here? Like, what does that even mean? Well, first of all, it is more difficult to determine. Okay? More difficult to determine. You need to know that. In fact, sometimes it is so hard to determine the convergence value that if you can figure out the convergence value, your name will go down in history as a famous mathematician. I'm not kidding. All right? So some of the sequences, or series, I mean, have names because so-and-so, Mr. or Mrs. so-and-so, discovered the convergence value of the so-and-so series. It's called the so-and-so series because of that person. All right? So just be aware of that. Nothing we're going to do here is simple. In this chapter, we'll discuss 2 main topics regarding convergence. 1, does the series converge? That's an important question, and it's hard to answer sometimes. Second one, if it does converge, what does it converge to? That question is sometimes almost impossible to solve. Okay? So as often as we can, we'll try to answer only the first question. All right? All right, first thing you need to know is what does it mean to converge? So in a sequence, you can tell it's convergent because the values look like closer and closer to something. A series converges when everything adds up to something. Okay? If the series doesn't add up to something, or it doesn't converge, then you call it diverge. So diverge just literally means doesn't converge, diverge. Okay? It does not mean that it's adding up necessarily to infinity, it just means you can't find the sum. There is no sum in the end. Okay, so let's take a look at some more things on this next page. If somebody ever asks you to find the value that an infinite series converges to, you tell them, say, okay, give me an hour and come back. Come back in an hour, and I'll have your answer, maybe. Okay? It's a really hard question. In math symbols, here's what you have to do. You have to first create a sequence of partial sums. This thing is called S sub n. Okay? S sub n. And it is not a1, comma a2, comma a3. It is this, a1, comma a1 plus a2, comma a1 plus a2 plus a3. Oh, I just lost something here. It was my eraser's going crazy. It's a1, comma a1 plus a2, comma a1 plus a2 plus a3, comma, and so on. So every term is harder to find than the last term was. It's a crazy sequence. Eventually you get to a term in the sequence that looks like this. He would be called the nth term, or the nth partial sum. But there's more after that too. And it just goes on forever. Okay, after you get the S sub n list figured out, then you try to create an explicit rule for S sub n. That is very challenging. And it's the hardest part. After you get the explicit rule, then you take the limit of that. So it's kind of a three-stage process. First, you construct a partial sum series. Then you write down an explicit rule for S sub n. And lastly, you find the limit. Now, if this limit is plus or minus infinity, or if it doesn't exist, then this series diverges. Okay, we'll definitely do example 1 and 2. We may or may not get to example 3. Okay, so the first thing I'm going to do is create a list of partial sums. So this is sort of my a sub n. Okay, so follow this closely. So first I'm going to make a little list. A sub n is 3 over 2 to the first. 3 over 2 squared. 3 over 2 cubed. 3 over 2 to the fourth, etc. Okay, so what I'm doing is making a little list, right? But this is not the sequence I'm really interested in. I need an S sub n list, okay? This is where it gets tricky. My first term in the S sub n list is the same as the first term in the A sub n list, okay? So the first term is easy, it's just 3 halves. The second one is basically 3 halves plus 3 fourths. So I'm supposed to add the first two together. 3 halves plus 3 fourths, combine it, right? So what is 3 halves plus 3 fourths? I got 9 fourths, you see. And then the next term is 3 halves plus 3 fourths plus 3 eighths. It's the sum of the first 3 terms. So 3 halves plus 3 fourths plus 3 eighths comes out to 21 eighths. And then I add the first 4 terms and I get 45 sixteenths. I worked this all out earlier. What a pain. That's step 1. Okay? Step 2, I'm trying to create a rule for that sequence. Okay, let's see here. I'm on to step 2. I want to create a formula that will generate a number in the second list. Okay, so it's a little bit hard to see. The bottom's not too bad. What do you notice about the denominator? It goes 2, 4, 8, 16. That's not too complicated. What's the denominator doing there? Doubling, okay. Isn't it true that the denominator is some power of 2 always? Starting with the first power of 2. So the bottom is always just simply 2 to the n. N is the counter, okay? So this represents 1, and this represents the second, and this represents the third, and the fourth term, and so forth. So the green numbers are related to the red fractions in the following way. The denominator of the red fraction is always 2 to the green number. Okay? The numerator is a little bit harder to figure out. It might help if I rewrote this numerator for you. If I wrote this as 3 times 1, 3 times 3, 3 times 7, 3 times 15, it might pop out at you more. Do you see it now? The top is always 3 times something. That something is always what? 1 less than what? The bottom. Yes. So this numerator resembles 3 times something. 3 times what? 2 to the n minus 1. That's step 2. And that's considered easy. This problem is considered a really easy one. And now we find step 3, the limit as n approaches infinity of s sub n. So you can use L'Hopital's rule. You could pull out the 3. In fact, I'm going to do that. I'm going to pull out the 3. I think this is a pretty simple limit. I think we can just do this in our head. This comes out to 3 times the limit of 2 to the n minus 1 all over 2 to the n. What happens when n gets very, very large? Here, this fraction goes to what? 1, right? Even if you plug in 5, it's 31 over 32. If you plug in 10, it's 1,023 over 1,024. So this is going to 1, and this limit ultimately is going to 3. And what we just figured out is this, guys. If you add up all the numbers in the s sub n list, and I mean all of them, even though there's an infinite number of them, if you add them all together, you get 3. So what do you get if you add 3 halves, 9 fourths, 21 eighths, 45 sixteenths, forever? 3. Interesting. So we would state that the infinite series converges to 3. Notice this is way harder than answering, does the infinite sequence converge? It's not a limit problem. This is constructing a new series, and then it becomes a limit problem. Much, much harder. Okay, so you can say the sum n equals 1 to infinity of 3 over 2 to the n converges to 3. Sometimes it'll be so hard to figure out the s of n formula that we will have to just simply say it converges and throw up our hands and walk away. It's just going to be that hard. All right? That one was considered easy. Let's try another one. This one, I think would be too hard. So I just would like you to show that this must diverge with a sketch. So first thing we'll do is treat this as a sub n, and we'll just jot down a sub n. If you plug in 1, you get a half. You plug in 2, you get 2/3. You plug in 3, you get 3/4. You plug in 4, you get 4/5. The partial sums would be a half plus 2/3, which is 5/6. Well, first starts with a half. The next one is a half plus 2/3, which is 5/6. Right? Then you add a half and 2/3 and 3/4, and you get 38/24. I didn't simplify yet. What do you notice? Let me make sure I added those first 3 correctly. 5/6 plus 3/4. Yeah, 38/24. What do you notice about these numbers? Like in the s of n list. This is 0.5. This is like 0.83. This is almost 2.0. There's 1 point something. These are growing, aren't they? So what's happening is, as we add together the a sub n values, you can show this with just a picture. Imagine if you had a box that had half a unit of area, and you tried to add to that a box that had 2/3 unit area, and add to that a box that has 3/4 unit area. What do you notice? Each box is what? Larger than the previous. So if you're going to do this forever, you're going to collect an infinite amount of area. So this picture kind of shows us that since each box was bigger than the last one, this diverges. Another way of saying that is the S sub n list is actually growing. That's a bad sign. That means this is going to diverge. So the picture shows that it diverges. These are increasing, and they're accelerating in their increase. And what we're going to do is we're going to just continue to answer this question. Do we think it increases? Do we think it increases? Does it decrease? Does it increase? Does it diverge? Does it converge? All chapter long until we hit Taylor series.